Раз, 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 раз. Ladies and gentlemen, дамы и господа, we start our morning session, and our first plenary speaker, Said Ali Khani from Iran. I am happy to see you here, Said. It is great pleasure for us.
Yeah. I think no need because online. Okay. Hello and good morning, ladies and gentlemen, and thanks for coming. First of all, I should thank the organizer, especially many people, Dr. Anna. I think I have write something here. You see here, I came from Yazd in the center of Iran with my car about 650 kilometers to Tehran. And we have a war with US and Israel, and many of international flight canceled. And I had to go to the Yerevan in Armenia and then Moscow. And then I received here last night about 11 p.m. And I'm so pleased to be here. Very nice place. Thank you to all of the organizer. Thank you. Thank you so much. Especially I should thank the Professor Alexander Kazakov, Mikhail Hachay, Professor Yuri, and Professor Anna. And also I am so happy to see my friend, Professor Elena, and also Dr. Hamid Reza Gol Mohammadi. Thank you. I would like to talk about graph theory. Actually, combinatorial optimization is about majority distinguishing coloring of a graph. And what is the majority coloring? All of you know what is the coloring. Mean vertex coloring of a graph is a map from the vertex set to a set, which I denote by capital C. C is set of the colors. And all of you know a vertex coloring is a proper if the adjacent vertices receive different color. And in this type, the coloring is not needed to be proper. And as an example, you see here a coloring of graph, which is not proper because these two adjacent vertices have the same color. But this is a proper coloring because every two adjacent vertices have a different color. And the origin of majority coloring, I think, come from this definition that is about unfriendly partition. And unfriendly partition of a graph is a map C from V to 0, 1, and -1 such that for every vertex X, the number of neighborhood of X which have the same color of X is less than or equal the number of neighborhood of X which have different color of X. And actually, Kwan and Emerson in an published work conjecture that the property of unfriendly partition into two sets should have true of infinite graphs. A counterexample to this was constructed by Milner and Shelah in 1990. By the construction use uncountably many vertices, leaving the countable case is still open. In the same article by Milner and Sheila, they showed that every graph does have an unfriendly partition in 3 sets. And there is this conjecture that does every countably infinite graph have an unfriendly partition in 2 sets? And this is an equivalent definition for majority. We say that age is a good one if different color assigned to its incident vertices. On the contrary, one age is a bad when it is monochromatic. And a vertex is happy when at least half of its incident age are good, and is sad if it's incident with more bad than goods. And this is, I think, the main definition and equivalent to previous definition of majority. A vertex coloring is a majority if at most half of the adjacent vertices of any vertex have the color C of V. So a vertex coloring is a majority if at most half of the adjacent vertices of any vertex have the color of the vertex V. And mu of G is the least number of colors that I need to color this graph with majority coloring. You see here, all of the vertices here are happy, means that at most half of the adjacent vertices of this vertex are the same blue. Okay, at most half of them have the vertex the color of vertex V. I know that most of you are applied mathematician, and my talk is in the pure mathematics and graph theory, but there are many applications of majority coloring that you see here. For example, in social network and opinion dynamics, communication networks and frequency assignment, distributed computing and load balancing, graph partitioning and Marx-Cut problems, and relaxed constraint satisfaction. And Lovász, very famous mathematician from Hungary, proved that every finite graph has a majority 2 coloring. And he applied this method that maximized the number of edges with different color endpoint. And also there is a definition for edge version. Similarly, we have this definition that an edge coloring C from E of G to 1, 2, and K is a majority K edge coloring if every vertex U of G and every color alpha in this set at most half of the edges incident with U have the same color alpha. And 2 years ago, Bach proved that every graph of minimum degree at least 3 has a majority for edge coloring, and every graph of minimum degree at least 4 has a majority 3 coloring. Okay, this is a majority coloring, and here I want to say something about the distinguishing coloring. This coloring started from Frank Rubinsky problem, I think in the Math Game Journal in 1979, asked this question that Professor X, who is blind, keeps key on a circular key ring. Suppose there are a variety of handle shapes available that can be distinguished by touch. Assume that all keys are symmetrically so that the rotation of the key ring about an axis is on the table from an examination of a single key. And this is a question that how many shapes does Professor X need to use in order to keep n keys on the ring and still be able to select the proper key by field. And you see a distinguishing coloring of a ring of 6 key here using just 2 color. One of them is red and another one is unpainted. And because of this problem, Albertson and Collins had this definition that is about distinguishing coloring or distinguishing number. The distinguishing number denoted by capital D is the least number of color D such that G admits a vertex labeling with D colors that is only preserved by trivial automorphism. Here we need automorphism of the graph. And we would like to color preserve only by trivial automorphism. And 19 years later, Raphael Kalinowski and Pilsniak had this definition about the age version of distinguishing number, which denoted by D prime of G. And this is the minimum number of colors that graph has age coloring with D color that is preserved only by identity automorphism. We know that automorphism of any graph is equal to automorphism of its complement G bar. So this is a very simple result that distinguishing color of any graph equal to distinguishing color of its complement. And the first papers in the subject of distinguishing coloring is about computing this number for famous graph. For example, you see here the distinguishing coloring of complete graph is n, and this bipartite graph k and n is n plus 1. And you see result for paths and cycles. And here you see distinguishing, age distinguishing coloring for path and cycle, and for complete graph and complete bipartite with the same size in each part. And you see here an upper bound for distinguishing index, which is at the capital delta, which is a maximum degree of a graph. And you see distinguishing index of complete bipartite graph, which is not easy to obtain, I think. You see, depend to D and D plus 1, and D obtained by this inequality. And after that, we could study these parameters for friendship graph. All of you know the friendship graph. Friendship graph denoted by f of n and is joined k1 and nk2. K1 and nk2. And you see here distinguishing number of friendship graph and age distinguishing number of friendship graph that is obtained by this ceiling number, and an is this number. And for example, for n book graph, this is a book. This age is a common age for all C4. If we have n C4, then we show by B sub n. This is a book graph. And you see here the distinguishing number of book graph and age distinguishing number of book graph. And we published, I think, more than 20 papers in distinguishing with my former PhD student, Samane. For example, you see here in the Philomath, in the Bulletin of Iranian Math Society. In this paper, we studied this parameter for natural and fractional power of graphs, which is very interesting, I think. Subject and discussion math graph theory in Poland is about this lexicographic product of two graphs. And here we studied an open problem proposed by Douglas West in famous book graph theory that characterized tree with distinguishing number 2, and also publishing communication algebra, stability of distinguishing number. And another product, for example, Turner product of two graphs. And for example, another kind of graph, such as planar and maximal outer planar graphs. Okay. And what is the majority distribution color? If I think it's a natural that we have both of them together, distinguishing coloring and majority coloring. We say this majority distinguishing coloring. We define this coloring last year. A coloring of a graph is a majority distinguishing coloring if the coloring is both distinguishing and majority. And the majority distinguishing number denoted by mu sub d and is the smallest number of colors for this kind of coloring. And you see the age version of this definition by some Polish. The age majority distinguishing number denoted by mu d prime of g and is the smallest number of color, which is both age distinguishing and age majority. Okay, here I have shown some example for P5. And these two colors are red. These two are red, these two are black, this two is black. So the minimum number of color that I need is 2. So the mu sub d of P5 is 2. And for every pass, we can color the graph as like you see, we need at least 2 color. But for age distinguishing, you see this color, this coloring 1, 2, 3, 1, 2. And we obtained these parameters for pass and cycle and many other graphs. Also, this majority distinguishing coloring have potential applications such as symmetric communication network, distributed computing, multi-agent system, social and communication networks, and theoretically significant. And here I present some of my our results, recent result. You see here the majority distinguishing number, which is mu sub d, is always greater than or equal distinguishing number, and obviously this is true for age version. And you see the majority distinguishing numbering for complete graph, and the complement of it is n, and for this star is n plus 1. And you see this number for pass cycle. This is not easy to obtain this number, but if you are interested, you can see in my paper in archive. I think this is in archive. The majority distinguishing number of pass and cycle, you see for vertex version is always is 2, but for H version is depend to number of vertices 2 and 3. And you see some example of this coloring here, which are majority distribution coloring. So we have many problems from here for majority distribution number and age majority distribution number. For example, we can ask very main question that what happened to this number when we remove an edge, we remove a vertex, for example, we have a two graph and product them, many product. These are many problems that we can think about them. And you see here, I am very interested to friendship graph because I think the friendship graph is very important graph because help us to prove a conjecture that I had in my PhD thesis in 2008. And this graph helped me to solve the conjecture. And you see the majority distribution number of friendship is exactly the distribution number of friendship graph. And this is for book graph, you see is depend to and be a perfect square or not. And for age version of majority distribution number of friendship graph, we have this formula. And also for book graph, we have this result that eta is this number. And as I said before, Douglas West proposed this question that characterize graph with distribution number 2 that I told them we characterize it in this paper. And here we propose this problem that characterize graph with majority distribution number 2. And we have this theorem that says that the trees with majority distribution number 2 and reduced at most 2 are P2, P4, P5, and T obtained by subdivision of two edges of K1 and 3. And here, I am interested to look at their product of graphs, and I like the corona, the corona of two graphs. I think all of you know the corona of two graphs, and there is no board to draw here. The corona of two graphs, we denote by this symbol that this is a slash circle. And if we had a graph G and below a vertex to any vertex of G, that we denoted this graph by this notation, G circ K1, and you see here the majority distribution number of this coloring. This coloring is less than or equal majority of coloring of G. And you see for some special graphs, such as Pn circ K1, we need two colors. For corona of C, and with K1 also, we have a majority exactly of Cn, and this is for Kn or K1. And if G is a connected graph such that G is not K1 and majority distribution number of G is less than or equal majority distribution of H, then we have this result that says majority distribution coloring of corner of the graph depend on H. That's H. It's not dependent to a structure of G. And here you see if G is a connected graph and majority distribution coloring is 2, then majority distribution of corner of the graph is exactly of majority of H. And if the majority distribution of G and H is 2, then also the majority distribution number of corner of G and H is also 2. And we have this theorem that says that mu sub D of K1 OH is, or this, either this number or this number, depend to majority distribution number of H. And here I want present some results about discoloring of polymer graphs, which is important in chemistry. Let's bring this definition first. Let G be a connected graph constructed from disconnected graphs G1, G2, and GK by selecting a vertex of G1, a vertex of G2, and identify these two vertices and continue in this manner inductively. For example, you see this is a polymer of graph, a graph which we can call polymer, and this subgraph are monomer in chemistry. Just we have some subgraph, primary subgraph, for example, G1 and G2 belonging in this vertex, and then G3, G4, and so on. As an example, you see here the graph Q, M, and M. What is a Q, M, and M? We have a complete graph Km, and in any vertex of this complete graph, we attach a complete graph Km. So I have M complete graph with n vertices. And you see the distribution number of this kind of graph is equal this number, the minimum of R, such that R times this R choose n minus 1 is greater than or equal M. And we could, to prove that the majority distribution number of this graph is exactly equal to distribution number of this graph. And here you see a barcode of the graph GI. This is also important for chemists and scientists of nano. You see we have some graphs, G1, G2, and Gn. And the barcode of G is the graph GI with respect to vertices xi is obtained by identifying the vertices x1, x2, xn. So we identify the vertex x1 from G1, x2 from G2, x3 from G3, and so on. So we have this figure, which is a barcode. And you see a result that is about barcode of graph, majority distribution number. The majority distribution number of barcode graph is less than or equal to the maximum of majority distribution of GI plus n minus 1. And this inequality is sharp. And you see I think equality holds for this kind of graph that we call it Dutch windmill graph. Dutch windmill graph denoted by D and K is the graph obtained by taking n copy of the cycle CK with a vertex in a common. The Frederick graph obviously is a special case of this Dutch windmill graph. And you see here the distribution number of Dutch windmill graph is obtained by this formula that the minimum of R such that this number is greater than or equal n. And we could to prove that the majority distinguishing number of this Dutch windmill graph is either the distinguishing number of D and K or D and K plus 1. And another family of graph you see here is circuit. The circuit is also important for chemists. The circuit of pairwise disjoint graph with respect to vertices xi is obtained by identifying the vertex xi with ith vertex of the cycle. We have a cycle Cn, and we identify this vertex with x1 from G1, the second vertex of Cn with x2 from G2, and so on. This is a circuit of the graph GI. And you see an upper bound for majority distinguishing coloring of G, and this upper bound is maximum of mu d GI and mu d of Cn. And also this upper bound is sharp. And finally, another family of graph which also important for chemists is chain of some graphs. We have some graph G1, G2, and Gn, and we consider xi in the intersection of gi and gi plus 1. And the chain graph of G of this n graphs as shown in this figure. So x1 is the common vertex from G1 and G2. X2 is the common vertex of G2 and G3, and so on. This is a chain of this kind of graphs. And if G is a chain of graph GI from 1 to n with respect to these vertices, then we have this upper bound for majority distribution number. And this upper bound is maximum of majority distribution of GI plus 1. And yes, this upper bound is also sharp, I think, but I am not sure which graphs satisfy this equality. And we have many open problems that I didn't have time to add to my presentation. Many problems there are in this new subject. As I said before, this is a very good question that what happened to majority distribution number when we remove a vertex or we remove an edge? What happened to this parameter? Or what about another product of two graphs? For example, many products, more than 70 products we have in graphs, and I think a very good question that asks, what about the Cartesian product, for example, of majority distinguishing coloring, lexicographic, and so on, many products, and also power of graphs. What about the majority distinguishing coloring of power graph, fractional power of graphs, and so on? There are many problems, and if you like to think about this kind of problem, just let me know to send you some question. And I invite you to visit Iran, especially my city, beautiful city, yes. You know, it's the oldest city in the world after Rome, Italy. This is the second one. And we have ancient architecture, world heritage, and warm hospitality. Thank you so much.
Thank you, Professor. Questions?
Thank you for your talks. Said you listed a list of several theorems. For me, it will be interesting. What is like the root part? What is the common techniques that used in the proofs? What is like a core idea? What they are based on?
This is not easy question. Because, you know, to obtain the distinguishing number of a graph it is not easy, because you should consider the automorphism group of a graph, how many automorphism have, and which of them does not preserve the coloring. Is not easy. If I had a board, I show just for pass. Here, I think in the majority distinguishing coloring, we must be careful distinguishing version more than majority, you know? And actually, we need to examine all of these results by computer also, okay? Python. Just first, we draw a small graphs, for example, P5, 6, 7, and so on, and obtain a formula, but we must check this is true or not, and we can check it by computer. If it's okay, then we can prove our results.
More questions?
Did you consider list versions of these colorings, majority colorings, distinguishing colorings?
Sorry?
The list versions, when you have a list of for every.
I didn't hear. Yes, it's another open problem. That
Nothing is known. Or...
No, I know, but we can define majority distinguishing list coloring of graph. This is a new coloring, but I think it's so hard to obtain results. I think, I don't know. I'm not sure. Thank you. I think Yuri. Oops.
Similar question. You consider this majority,
Yeah.
say, principle, so it means half.
Yeah.
And if you consider some other number, so what, are there any results?
No,
If
we
you don't consider half.
No, I think nobody considered this one, but very good question. That, for example, third, yeah, yeah. Good question.
Good question.
Very nice. No. Good question. Many there are. If editor accept this definition, then we have many problems to solve. Thank you.
No questions. Thank you, Professor, again.
Thank you so much. Thank you. Thank you.
Now we have a break, and after 20 minutes, we continue in different places, not only here. So you have time to move to another place.